All right, guys, let's pray. Father God, we thank you, Lord, for this day. We praise you, Father God, for your goodness, Lord God, and your love for us, Lord God. We pray, Father God, you bless this day. Make it yours. Make it whole, Father God, for those students, Father God, who are everywhere, all over the country, Lord God, who are tuning in, Lord God. And I pray, Father God, just that you just touch them, Father God, and keep them safe from any hurt, harm, or danger, Lord God. Just guide us, Lord God, to your perfect will for our lives, Lord God. Pray, Father God, that you give me the words you have me to speak, Lord God. Give us all listening ears. In Jesus' name, amen. All right, well, welcome back again, guys. Let's get started. We're going to be in section 4.7 today, talking about Gaussian quadrature. Gaussian quadrature. Okay. Now, this is another way of being able to approximate a definite interval. So just another method to be able to approximate a definite interval, right? So if you guys remember from before, what we did when we were dealing with left endpoint method and trapezoid and Simpson's method, is that I had a function and I decided where I was going to place my nodes. So they were usually equally spaced. So I have x0, x1, x2, x3, x4, x5, x6, x7. So I would have my nodes placed, and then I would approximate my definite interval based off of that information. So maybe I would do something like a trapezoid method approximation, something like this. So I would connect the lines. Oh, missed it. Right? And then I would look at the area underneath this trapezoid, right? This composite trapezoid shape. However, the thing is, well, is that the best way? Is that the right way to approximate a definite interval? Are there other ways of doing it, right? Here I am assuming that I know the best nodes to choose, right? I equally space them, right? But what I should really do is I should let my function decide where I should place these nodes. Let my function, the function that I'm trying to approximate, let that function decide where these nodes along the x-axis should go, right? And that's the idea behind Gaussian quadrature, right? I'm going to let the function decide where I place these nodes. So let's look at how this is set up. In Gaussian quadrature, the weights C1, C2, Cn, and nodes, here I have x1, x2 through xn. We usually start at x0, are chosen so that the integral from a to b of f of x dx approximated by c1 f of x1 plus c2 f of x2 plus dot 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 cn f of xn has the minimal possible error. So what we're doing, we have this approximation. So before, if you guys remember from our previous class, right, we had the left endpoint method, the right endpoint method, and Simpson method, and essentially all these methods are just my function values multiplied times a constant. When it all comes down to it, all those methods are function values multiplied times a constant. So here I have my function values, and I have my constants that I'm multiplying by them. And I'm trying to pick the constants and my nodes, the places where I'm going to essentially separate my subintervals, I want to pick those so that my error between my actual definite interval and my approximation, that error is as small as it could possibly be. Small as it could possibly be. And so let's just start off with something simple. For instance, it is possible for n nodes and weights to be chosen so that a 2n minus 1 degree polynomial definite interval has no error. Has no error. It is possible for n nodes and weights to be chosen so that a 2n minus 1 degree polynomial definite interval, the definite interval of a 2n minus 1 definite interval of a 2n minus 1 degree polynomial has no error. I'm going to actually switch that around so that the definite interval of a 2n minus 1 degree polynomial has no error. Let's actually show that this is possible. Let's look at an example. Let n equal let 2n minus 1, let the polynomial be a third degree polynomial. Okay. I want to be able to approximate this third degree polynomial. Let's say a naught plus a sub 1x plus a sub 2x squared plus a sub 3x cubed dx, exactly using how many nodes? So that we need to figure that out, right? I want to be able to approximate this polynomial exactly using a certain number of nodes. So let's see, if we deal with a third degree polynomial, so we have 2n minus 1 equals my degree of my polynomial. So 2n minus 1 equals 3. So 2n is equal to 4, so n is equal to 2. It should be possible, unless I'm lying, right? It should be possible for me to be able to approximate this third degree polynomial using 2 weights and 2 nodes. What does that mean? I should be able to do something like this. I should be able to do c1, x1 plus c2, x2. I should be able to choose x values, and I should be able to choose constants so that I'm able to approximate, it should be c1 f of x1 plus c2 f of x2. I should be able to choose x1, x2, c1, and c2, so these two guys are exactly equal to each other. You say, what magic is that? How can you use just 2 points to approximate the definite interval over for any cubic polynomial you can think of? That seems like it's crazy, but it's not crazy. Not at all. How can we do that? Well, for the sake of, to make life a little bit easier for us, although we don't have to do this, let's say we're integrating from -1 to 1. So let a equal -1, B equal 1. It doesn't really matter what A and B are, but it'll make it a little bit easier to see kind of what's going on. So A is equal to -1, B is equal to 1. And so what I can look at this, I could actually say, all right, this is from -1 to 1, A0 plus A1x plus A2x squared plus A3x cubed dx has to be equal to this. And I'm going to actually use something that we have from linear algebra, right? Linear algebra, we can think of this polynomial being generated from a basis of 4 functions. I have the function 1, the function x, the function x squared, and the function x cubed, right? All of these, a constant function, an x function, an x squared function, and an x cubed function is the basis to be able to generate any polynomial of degree 3 or less, right? So what we can do is we can say, okay, we can solve the above equation by using the system. Where I'm going to look at my constants, my x squared terms, and my x cubed terms. Now my constant basis is essentially just 1. So I can say the integral from -1 to 1 of 1 dx, right? If this statement is true, it should be equal to c of, well, in this case, my f of x is going to be 1. So let's write it this way, so you can see it a little bit better. I'll say that my f of x is equal to 1. Okay. And here my f of x is equal to x squared. F of x is equal to x squared, x cubed. Is equal to c times, well, if my f is 1, right, so think of this as my first basis function. So if f is 1, then what happens when I plug 1 in as x1 into my function? I get the value of 1. Plus c2, I plug x2 into this function, I get the value of 1 again. Okay. So essentially what I'm trying to say is I want to, if this is going to be equal to this, then 0th degree polynomials have to also be exactly equal, right? So if a cubic is going to be equal to cubic degree polynomial is equal to the right hand side, I should have 0 degree polynomials equal to the right hand side, 1 degree polynomials equal to the right hand side, 2 degree polynomials equal to the right hand side, and 3rd degree polynomials equal to the right hand side. If I plug in, if my function is x, right, 1st degree polynomials, right, then I have to have the integral from -1 to 1 of x dx has to be equal to, my function is x in this case, so I get c1 x1 plus c2 x2. Okay. Then I plug in my function, I have my function x squared, right? So I'm dealing with polynomials of degree 2. So that means that if this statement is true, then I should have that -1 to 1 of x squared dx should be equal to c1 x1 squared plus c2 x2 squared, because my f of x is x squared for this particular one. And finally, x cubed, right? So I have my x cubed term. So if this statement is true, then also the integral from -1 to 1 of x cubed dx has to be equal to c1 x1 cubed plus c2 x2 cubed. Okay? This is that last condition right here for this one right here. So I have 4 equations. And 4 unknowns. My unknowns are C1, C2, X1, and X2. What I'm trying to say here is that we have to think about this in terms of linear algebra, right? What I can do is I can multiply this number, I can multiply 1 by A0. I can multiply this X by A1. I can multiply this X squared by A2. And I can multiply this X cubed by A3 and then add them together. And that whole thing should be equal. When I add this side, and if I add all 4 of these equations together, this, and multiply by those scalars, should be equal to the right-hand side. That's what I'm trying to say. And if I had more time, I would show it to you guys. But we don't. So I have 4 equations and 4 unknowns. So if I have 4 equations and 4 unknowns, I can solve this system. I'm just going to plug it into my calculator and tell me what it's supposed to be, right? Before I do that, though, let me just rewrite the system over here. My system is going to be 2 equals C1 plus C2. 0 equals C1 X1 plus C2 X2. The third one is 2/3 equals C1 X1 squared plus C2 X2 squared. And the last one, 0, is C1 X1 cubed plus C2 X2 cubed. And so what do I get when I solve this system? Right, solve it using my calculator. You can too. I get that C1 is equal to 1. C2 is equal to 1. Amazing. X1 is equal to negative square root of 3 over 3. X2 is equal to square root of 3 over 3. So these are my weights and these are my nodes. So here are my weights. Okay, they're equal. And then these are my nodes. And what does this mean? What does it all mean? If I have a cubic polynomial, okay, on an interval from -1 to 1, and I want to be able to find the area underneath this function. Right? I want to find the area underneath this function. Only thing I have to do is evaluate my function at negative square root of 3 over 3 and at positive square root of 3 over 3 and add them up. Find out what my value is here, what my value is here. That's the answer. That's crazy. Let's look at an example. Before we put that example, so we have our first quadrature. I'll put it here. Integral from -1 to 1 of A0 plus plus a1x plus a2x squared plus a3x cubed dx. This is equal to f of negative square root of 3 over 3 plus f of square root of 3 over 3. This is it. And this will be the value of the polynomial exactly. However, if I wanted to, I could approximate any function using this as well on interval from -1 to 1. So from -1 to 1, from -1 to 1 of f of x dx, I could say that it's approximately equal to this. I can't guarantee, I cannot guarantee that it'll be equal to it unless it's a cubic polynomial or less. But I know that it's going to be approximately equal to that. And this is Gaussian quadrature. All right. I hope that sort of made sense. Sort of, kind of. I can see some people shaking their head, no. But the application of it is really cool. Let's look at an example. Let's approximate the interval from -1 to 1 of 4x cubed plus 2x squared minus 5x plus 1 dx. And the interval from -1 to 1 of e to the x dx using Gaussian quadrature. My n is equal to 2. And the trapezoid rule. Okay. Let's approximate -1 to 1 of 4x cubed plus 2x squared minus 5x plus 1 dx and -1 to 1 of e to x dx using Gaussian quadrature n equal 2. That's what we just got to be doing, right? We use 2 points and the trapezoid rule, right? Which is also a 2-point method, right? So we look at A. Before we do that, what is the exact answer for both of these guys? So -1 to 1 of 4x cubed plus 2x squared minus 5x plus 1 dx. Let's find out what's the exact value of this. Let's look at that. Let's see, what do I have down? Mr. Calculator, you told me it was 2/3. And the interval from -1 to 1 of e to the x. It's about 2.3504002. And it keeps on going. Okay. So now we know what the exact answers are, right? So let's look at A. Well, there is no A, but we'll just say, what do we get for Gaussian quadrature when we do it? Suppose we want to be able to integrate, we want to approximate -1 to 1 of 4x cubed plus 2x squared minus 5x plus 1. Okay, so let's plug that in. 4x cubed plus 2x squared minus 5x plus 1 dx. This is my f of x. And I want to evaluate at f at negative square root of 3 over 3 and at square root of 3. And when I plugged it in to my calculator, right, this function f of x, right, use the such that symbol, I get 10 over 3. Try it out for yourself. See what you get. What happens when I plug in e to the negative x, right? So I change functions. So e to the x, right? Not e to the negative x, e to the x. So I go from negative 1 to 1, e to the x dx. Here's my f this time, right? My f of x. Plug in negative square root of 3 over 3 and square root of 3 over 3. And what I got when I did this one is 2.342696. 2.342696. That's not a bad approximation. Is it great? No, it's not great, but 2.34296 is not terrible at all for Gaussian quadrature. Let's do the trapezoid rule. So B, trapezoid rule. All right. My h is equal to 2, right? Just making sure because we're going from negative 1 to 1. So I have 1 minus a negative 1, which is 2. We're not splitting it up. We're not doing the composite rule. We're just doing just a regular trapezoid rule. So negative 1 to 1. Oh, I should be using approximately equal to, right? I know that these guys are going to be exactly equal. That's why I used the equal sign here, because I knew they were exactly equal. But for e to x, they're going to be approximately equal. Same thing for the trapezoid rule. We have negative 1 to 1 of 4x cubed plus 2x squared minus 5x plus 1 dx. My f of x is still this guy right here, so I have 2 over 2 is my h. Here we have f of our first point, which is negative 1, plus f of 1. And when you do this one, when you work this one out, you get your value to be, what do I have? 6. What is 10 divided by 3? 10 divided by 3 is what? About 3 it's a 3 1/3, right? 6 is way off. That is way off. That's terrible. 6. That's quite bad. That is awful. But 6 is what we get. At least that's what I got. But it messed up. Right? But it makes sense. Gaussian quadrature is going to give us the exact value of any cubic polynomial. But I have to just make sure that I pick the values of x1 and x2 to guarantee that I get that. And what about e to the x? How well does it do with that one? Okay, same thing. 2 divided by 2. F of -1 plus F of 1. Again, this is going to be my F, right? E to the x is going to be my F here. When you do this, when you get 3.086161127. Again, this one's pretty bad, pretty rough. Not a good one at all. Okay. So this is the idea behind Gaussian quadrature. And it's a trapezoid rule, right? And this is Gaussian quadrature where n is equal to 2. There is a Gaussian quadrature for n equal to 1. Does anybody know what that is? Gaussian quadrature for n equal to 1. That is actually the midpoint rule. So the midpoint rule. Midpoint rule, right? This is a Gaussian quadrature. For n equal to 1. Now, for what polynomials would it be exact? For what polynomials would it be exact in Gaussian quadrature? Now, some of you guys are like, what is the midpoint rule, right? The midpoint rule, so you have a function from A to B. The midpoint rule, you take the middle value, A plus B divided by 2. Use that as your approximation over that interval. It's the midpoint rule. So the midpoint rule, if you have the interval from A to B, f of x dx, that's going to be approximately equal to f of a plus b divided by 2 times h. And so this is the midpoint rule. For what values of, for what polynomials for what degree polynomial will the midpoint rule be exact? And the answer is, we just do 2n minus 1. So exact for 2 times 1 minus 1 degree polynomials. Meaning that this guy is good for first degree polynomials. First degree polynomials. I know when I deal with the midpoint rule, I know that, what do we have? That I have, I'm having one of those days, the integral from, we say a to b of f of x dx, a naught plus a1x dx should be equal to f of a plus b divided by 2 times h. Okay. And I'm just making sure that got all of that down. All right, so that is Gaussian quadrature, and now we can extend that idea too. I'm trying to remember if the midpoint rule has a 1/2 in front. Let me look that up real quick. Bear with me, guys. I'm going off of memory, and Dr. Weston's memory is not that great. So let's keep going. All right. If it's not right, I'll make another video talking about it, but I think it's right. Trying to remember stuff, but I think that's right. I hope it's right. All right. So let's see. I wanted to talk about, before we finish, let's talk about just extending this to, we have n equal to 1, we have n equal to 2, Gaussian quadrature. Here's another one. Gaussian quadrature. For n equal to 3, this one I have written down. And it's this. And so if n is equal to 3, what's the degree of the polynomial that you can exactly approximate? Let's find out what that would be. That would be 2 times 3 minus 1. And that's going to be 5. So 5 degrees. Bear with me. I'm sorry. I'm a little bit tired. I apologize. I apologize. 5 degree polynomial. And so what's the Gaussian quadrature for this? And some folks will just go from -1 to 1 again. A sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the 4th plus a sub 5x to the 5th dx is exactly equal to 1 over 9 times f of negative cube root of 3, f of negative the cube root of 3/5, okay. F of negative cube root of 3/5. So the 3 and the 5 are all underneath the, let me say this again, 1/9 times the quantity f of negative the square root of 3/5, plus 8 f of 0 plus f of the square root of 3/5. And let me rewrite this because this is still not right. Still not right. Again, I apologize. Let's do this again. From the top, I'll get it right this time. 1/9, and I'm going to get a different marker too, and make me feel better. One that has a little bit more juice in it. Do I have any markers with any juice in it? I use too much. 1/9, this one has just a little bit. 5 times f of negative the square root of 3/5. There we go. Plus 8 times f of 0 plus 5 times f of the square root of 3/5. All right, so here's our guy in all its glory. So a 5th degree polynomial is equal to, I can approximate the definite interval of a 5th degree polynomial using only 3 points. in the interval from -1 to 1. That is insane how useful that is, right? So imagine if you have to do multiple computation where you have to integrate polynomials of 5th degree or higher, right? Instead of integrating the polynomial over and over and over again, right? All you need to do is to just evaluate at those particular locations, right? That's all you have to do. If you're always dealing with 5th degree polynomials, there's no need for you to integrate that and then evaluate it at the points. Just pick those 3 points, and then you're good to go. Add them together with the right weights. Let me do an example with this, and then I think we're going to be good to go for the day. I want to approximate. And I think this is going to be the last video that I'm going to do today. I want to approximate the integral from -1 to 1 e to the x cosine of x dx using a n equal to 3 Gaussian quadrature. An n equal to 3 Gaussian quadrature. Okay. So if you plug in, all right, here I have my function f of x, right here. I get 1/9 of 5 times this function, evaluated at negative square root of 3/5 plus 8 times f of 0 plus 5 times f of square root of 3/5. Really no need to write it again. Just wrote it so you can see it one more time. So did Dr. Mercer write it down right the first time correctly? And when you do this, you get, at least I have 1.9. So this should be approximately equal to. I get it to be 1.93339 is what I have in my notes. Let's see what the actual value is. I'm going to look it up. I haven't typed it into my calculator. Let's see what it is. Let's find out what it is. Integrate e to the x times cosine of x. Okay. X goes from -1 to 1. The actual value when I integrate this in my calculator, I got to be 1.9342. This is a pretty good approximation, I would have to say. This Gaussian quadrature gave a pretty good approximation of e to x cosine of x, just using 3 points. Just using 3 points. So Gaussian quadrature can be very useful stuff. And so that's all I wanted to say about this. I think we're going to just stop it there, and we'll pick up with another section where we'll be in solving differential equations numerically. Right? So that's what we're going to be doing next time, but not today. I think I'm done for the day. So I hope you guys are having a wonderful evening or morning or whenever you're watching these videos, and miss you guys, and I hope you guys are having a great day.